Hi everybody, and welcome to the next lecture on video coding. This time about transform coding, analysis, and also synthesis. So last time we saw how we can apply transform coding to our image blocks and how to invert the transform for the decoding process. We also saw that we can interpret the transform as a special case of a filter bank. For the analysis, the filters appear as columns of the transform matrix, but in reverse order. How does the equivalent filter bank look like for the synthesis? So for the synthesis, we saw that we have the equation x equals t inverse transpose times our transformed block times the inverse transform matrix. So in this way we apply the inverse transform to the rows and to the columns. So now if you look at a synthesis filter bank, we first upsample our subband signals by our downsampling factor n, which in this case synthesis becomes an upsampling factor of n, and then filter them with our synthesis filters. Remember, when we do the upsampling, we have more bandwidth available, and this additional bandwidth is filled by spectral copies. And those spectral copies create artifacts if we don't filter them. So that's why we have to filter, bandpass filter the corresponding signals to basically fish out or filter out the correct band, the correct frequencies. So the following picture shows a one-dimensional synthesis filter bank, just to make it easier to depict. So this is the decoder with critical sampling, and lowercase m here is the block index, so the index at the lower sampling rate, and the y corresponds to one row or one column of our transformed coefficients. So here you can see it in this diagram, this block diagram. So the y's are now our subband values for block m, lowercase m. And in the synthesis filter bank, then we take those sequences of those different blocks. So we get a coefficient for each block. So for the sequence of blocks, we get a sequence of samples here. And then after each coefficient, we insert n-1 zeros to obtain the original sampling rate back. So here we have the spectral copies, and then we just need to filter out the correct spectrum, the correct position, using our bandpass filters. So here, beginning with a low-pass filter, and then we have bandpass filters, and the lowermost one is a high-pass filter. So then we have spectral components, and we need to add them up to get the reconstructed signal. So at the output, we would have our reconstructed image, right, at the original size. Yeah, so in this block diagram, we can see that we obtain the impulse response of our filter HK by inputting an impulse in subband YK and zeros in all the other subbands. So it's an easy trick to test a filter bank, and it also works in this case for obtaining a result here using the theory. So we can just put in one sample with a value 1 in here subband K, and for block 0, right? And everything else is set to 0. All the other subbands are set to 0. So now we can apply this impulse function as vector y to our transform implementation, and we get y times t inverse, right? And the result should be the same as coming out of our equivalent synthesis filter bank, right? So now we can view the synthesis transform as a matrix consisting of these row vectors. So this is now t inverse, And here we have the first row, T0, the second row, T1, and so on. And remember, this y only contains one element with value 1, and the rest is all zeros. And if you multiply it from the left-hand side, that means we only keep one of those rows, and the rest is basically multiplied with zeros, and hence the result of this multiplication is then that we just keep the kth row. So we have sub and k here. So after multiplication here with this inverse matrix from the left hand side, the result will be the kth row. Right, so this is the result. So here what comes out of this case of having just one subband unequal 0 is simply the kth row. So if the kth subband is unequal 0, has a factor of 1, then we get the kth row. So now we can see that the impulse response of our kth subband filter of our transform is its kth row, but now not reversed in space or time, unlike the analysis. Right? Remember, when we input an impulse in our filter bank, going back to our diagram, here we just input a 1 for the kth subband, then we get the impulse for this, the impulse response for the kth subband, because all the other inputs are 0. Right? So we take a 1. Upsampling this 1 doesn't really change much because we just append zeros. And then the output here will be just the kth subband impulse response. So that's easy to see. So we do the same here for our transform implementation, and out comes the kth row of our inverse transform matrix. Right, so that's easy then to memorize. For the synthesis, the impulse response of our kth subband filter of our transform is simply the kth row. Right, and since we don't have to reverse, it's even simpler as for the analysis. So again, we find that we have filters of exactly the transform length capital N. Right, that comes because that's the size of our matrix. Observe that for T transpose inverse, we obtain the equivalent impulse responses in the columns, since it is the transpose matrix. So in conclusion, we obtain the equivalent synthesis filter bank impulse response by reading out each row of the synthesis transform matrix, now not reversed. To know the equivalent impulse response has the advantage that we can analyze them, for instance by looking at their frequency responses by applying the Fourier transform or the function frexy to them. So here, this is the Python function. So this is what we want to do next in this Python example. So again, we take the DCT2 as our transform matrix, as common in image processing. And we use Python and import NumPy and SciPy FFT pack. So let me start here with Python. Python 3 should work. And we make our identity matrix, in this case for the size of our matrix of 4 by 4. And then we obtain the transform matrix for the DCT type 2 by taking the function DCT and the argument I. Remember, the function DCT internally has this transform formula, but with a fast implementation. So in order to get this matrix, we simply, as an input, as the argument, specify the identity, and then the function implicitly computes I times t, identity times t, so the output must be t. Right? So usually in an implementation, we would not really need capital T, but here we need it for the analysis, right? For the implementation in a video coder, you would simply specify your image block here as the argument. But since we want to analyze our frequency response, we need this matrix T. So this is now our matrix T. Here we turn it into the matrix type T, simply to more easily obtain the inverse. Strictly speaking, we wouldn't need to turn it into this matrix type. It's just convenient here for the sake of this example. And this is then the resulting matrix. So this is the DCT type 2 transform matrix for size 4 by 4. So you can see here, first column is the first impulse response reverse. So this is the low pass. Here is the next band pass. Here's the next band pass, and here's the highest band pass, which is the high pass. So let me do it here in a Python shell to show you. So we're starting in with Python 3. And now we can import numpy as np, import scipy.ffmpeg, and then I equals np.I of 4. So this gives us the identity matrix. So this is the identity matrix. And then we compute our transform matrix. So using this row here, we just copy and paste it. And then we have T. So here we get those numbers, but now I turn it into the matrix type, np.matrix of T. So now we have the same number, but as a matrix type. Yeah, so now we can compute the inverse matrix, which is used for the inverse transform in the decoder. So here, this makes it very convenient. In the matrix type, you just have capital T dot I for inverse. Right, so the dot I is the inverse of this matrix. So again, object-oriented notation. Dot I is the function of the object T. So I can do it here. T inf equals T dot I. So T inf. So this is now our resulting matrix. So now you can see it looks actually very similar to the forward transform, but here the low pass filter is indeed in the first row now. So this low pass filter actually is identical to the analysis low pass filter with all those 0.5s, but now it appears in the first row instead of the first column. So also the second one, here we start with 0.65, compare that with the analysis, and here we have minus 0.65, because here we have to start from the bottom, right? Bottom up. So here we have now plus 0.65. Then here we have the next filter, 0.5 minus 0.5, compare it, 0.5 minus 0.5 minus 0.5. So here it's again identical. And then the last one, the high pass filter, 0.27 minus 0.65. Here, 0.7 minus 0.65. Yeah, except that here we have to start from the bottom, right? So here again we have this sign flip. And or we could also see or say that the relationship between those filters in the synthesis to the analysis is simply that the synthesis impulse response is simply the time flip version of the analysis impulse response. So here we have to start at the bottom, but if we would start at the top, you would get exactly the same. So here T inverse basically is the transpose T, right? And this is actually in general the case for orthogonal transforms like we have for the DCT, right? For the DCT, in general, when we use norm ortho, norm equals ortho, that means that inverse is the transpose. And for the impulse responses, this means that the impulse responses for analysis and synthesis are the time or space reversed or the flipped versions of each other. Right? Yeah, so observe that the inverse matrix is identical to its transpose, right, what I just said. This is because the DCT2 transform matrix is orthogonal. The transpose needs a factor to become the inverse, or orthonormal, the transpose needs no factor to become the inverse. So that's because we chose norm equals ortho. Here we can see that, for instance, the first row contains the impulse response of the first synthesis filter, which here indeed is identical to the first analysis filter. Or take the second subband, H1 of n, as an example. In the analysis part, we have the equivalent impulse response of the second analysis filter. So this is what we just looked at. So here's the second row. And the second synthesis filter is obtained with a second, well, this was the second column, right? And this is now the second row at the synthesis. And we can see that this second synthesis impulse response, this row vector, is the time reverse or the flipped. It's not necessarily time, so maybe I should remove the time because we are in the space domain. So this is the reverse version of the second analysis impulse response, which is a column vector. Observe that this is generally true for orthogonal transform matrices, where the synthesis matrix is the possibly conjugative complex transpose of the analysis matrix. Yeah, so taking again our subband block Y from our previous example. So there we had our very simple image block of all 0.3s, right? Here we have 4x4, a 4x4 matrix, and the entries are all 0.3s. Then we transform it, rows and columns. Here, T from the right hand side, T transpose from the left hand side. Here now I'm not taking the matrix type, but the array type. That's why I have to take the function dot. And this is what we got. Right, so this is what we already saw last time. Let me do it again here in my little terminal shell. So here you go. And this is the Y. Looks a little bit nasty. Maybe I need to make this window a little bit bigger. Still doesn't quite fit. So the window just has to be wide enough and it should work, but it doesn't. Interesting. It's not using the space that I'm giving it. Oh well. So in any case, you can see here we get the largest value here on the upper left hand side. So this is the first entry, 1.2. And interestingly enough, this is not exactly 0, but 10 to the minus 17 or 10 to the minus 32. So this is again in artifact, a rounding error from away from 0. So remember that Python has about an accuracy of 10 to the minus 16. So anything in that order is practically 0. Yeah, it's kind of funny. If you do it in Python 2, you get exactly zeros, and if you do it in Python 3, you get those tiny rounding errors. Yeah, so here's now the inverse. So here we see the Y, and we multiply the Y with the inverse of T from the right hand side, and the transpose of the inverse from the left hand side, and we get the original back. So let me try it here in my terminal shell, paste, and this is what we get. Right. So here we are actually getting the matrix type because the tinf was the matrix type, so it automatically converts to the matrix type. So here we see that we indeed get our original block back, the 4x4 matrix with values of 0.3. Here I'm also observed that the inverse of the T transpose is the same as taking the inverse first and then transposing. Here also observe that the beauty of this approach is that we can deal with each block of our image independently of the other blocks, meaning that there is no overlap of filters into neighboring blocks. So subdividing our image in 8x8 pixel size blocks allows us to, in this way, each individually, treat each individually using our transforms. So that's convenient for processing, since there's no dependency between neighboring blocks. But on the other hand, we saw that this leads to blocking artifacts. So has advantages and disadvantages. Yeah, so what's the place of the transform in a complete image or video coding system? So the following two blocks block diagrams show where in an image or video coder the transform appears. Observe that it is applied after the color transform and the low pass filtering and downsampling. So when we have the color transform, we have the component Y, and then we have the components CR and CB, and they are downsampled by first applying a low pass filter and then the downsampling. And after that we apply our 8x8 DCTs. Yeah, and here in this picture, DCR and DCB denote the downsampled color components, and the subscript DEC denotes the decoder versions. So here's the block diagram of the encoder. So here you can see our frame coming from the camera, having those three primary color components, RG and B. And then we do the color transform. We turn it into Y, CR, and CB, which you can see here. The luminance and the two chrominance components. And then the CR and CB components are low pass filtered, followed by downsampling. So this is usually the 4 to 0, meaning the downsampling by a factor of 2 horizontally and vertically. This leads to DCR and DCB. So these color components have half the size horizontally and vertically, but still we apply 8x8 size DCT blocks to each. So then we have those DCT coefficients for all our 8x8 blocks, and we store them or we transmit them, right? So that gives our compressed file after quantization and after entropy coding. So this is not shown here. So here's just, we are ending with DCT coefficients, but in practice we would actually take the lowest frequencies, for instance, quantize them, and then entropy code the quantization indices to obtain our bit stream or a compressed file. Yeah, and then in the decoder we simply have the reverse steps. We take our compressed file or our bit stream, we apply our inverse entropy coder to it, then the inverse or the reverse quantizer. We dequantize our values to get our original quantized values back. Then we have YDEC, DCR, DEC for decoder, and DCB. we upsample them. Then again, we need to do the low passing for smoothing the image. And then we have our full-size components back. CR deck and CB deck now have the size of the original image, as does a Y deck, never changed. And then we do the inverse color transform, YCRCB back to RGB, and this RGB can then be displayed on our display. Okay, so that should be it for now. So thanks for your attention and see you in the next part.